My shirt. Should I just wear it like it is?
I'm just gonna give you Bree or Emily's shirt.
Okay.
So just come by my office.
Okay.
Because
When
they don't deserve a shirt. Especially Emily.
When would you like me to come get it?
That's a good question. Just come by anytime I leave with Vicky.
Okay.
If I'm not there, she'll have it.
All right. Thank you.
I don't know what size theirs is. What size did you have?
Medium.
I think that's what they had. But the two of them have totally ditched me this semester, so I'm not too worried about it.
We started out with a big class in here for calculus. I was actually surprised how many people wanted to take it. Now we're down to 6.
There's going to be another big class in the fall.
For Calc 1 or Calc 2?
Calc 1, like next fall.
Or next one.
Because we have 24 people already signed up for trig in the spring class, which is huge.
I like free calculus. I miss free calculus.
I like this Google stuff.
I don't know how to connect the dots. Like, I understand the stuff we're doing in class, but then he talks about how it's going to relate in the future, and I'm just like,
Well, it's all area under the curve, all of it.
but I don't see how it all ties into that. That's not
You don't see how the summation does?
Mm-mm.
Adding up all the rectangles under the curve is just all of the area under the curve.
But how are we getting these
Oh, I
weird
guess I gotta turn my
equations that are elaborate? I don't understand how that's...
You'll learn that in real analysis.
That doesn't sound hard at all.
That is a hard class, I'll admit. That's like, after you get to Calc 3, then in real analysis you learn how to prove everything that you didn't learn in Calc. Why would you do that? It's just some more in depth. It's like pre-calc, you learn all the stuff, and then in calc you learn how to prove it all, or some of it. And then what you don't learn how to prove in calc, then you learn it in real analysis.
Oh. So it's like this never-ending circle of you learn it, you prove it in the next class, but you also learn something new, and then
Pretty much, yeah.
you learn something new.
Real analysis is like nothing but proofs.
Gross.
Yeah. And then you get into complex analysis.
Complex.
And then you can take like knot theory, chaos theory.
Did
That's
you
like
take
grade
all of
school.
these?
I didn't take chaos theory. I took complex analysis, I think 1 and 2. I took a really good operations research class, which is like a modeling class, which is kind of more my style because I'm more application, not proof and pure math stuff. I need to apply it to something. But it was cool, like we redid the whole bus stop route for Watauga County Schools. It was awesome.
There's math involved in that?
The efficiency of your routes.
Oh,
Oh my.
It was awesome.
You get like speed limits and stop signs,
Yeah.
whole 9 yards.
Yeah, at the time it takes for kids to get off the bus and how many kids are getting off the bus.
That depends on what age it is, because I think high schoolers get off the bus a lot faster than little preschoolers who like just kind of dawdle along.
I mean, it was,
They're so
it was
sneaky when
an
they
awesome
walk.
class.
So fun.
You were so smart, Miss Clean. If anything, if I had to take a pre-calc class again, I think I'd do great.
Yeah, if you had to take calculus again, you would do great.
I hope. I'm probably gonna have to take it again in a 4-year school just to be prepared for what Calc 2 would be like at that school. So I'm just glad to have the knowledge down in these times.
I mean, when you really learn it is when you start teaching it.
I don't know if I could teach it.
I don't.
That's when
think
you
so.
really have to learn it, because you have to be ready for whatever questions come up, and so you kind of have to do it backwards and forwards.
Well, I have to take Calc 1, 2, and 3, and then differential
I
equations.
don't have to take 4 also.
No, 4 is replaced with the differential
Differential
equations.
equations is fine.
My dad said he barely escaped his life.
It wasn't the fun math was good. I think it was.
And it doesn't make me feel good knowing that whenever he looks at my calculus homework, he's like, oh, that's easy stuff. I'm
Thanks, Dad.
like, all right.
Discrete math was fun.
Discrete. Is it discrete?
It's like logic.
This works
I like
because
logic.
In this.
like
So
all the
they
other
might
ones.
have to pick me up for my house, but I don't
Yeah.
know for sure.
On Saturday?
We don't have diamonds in for that. But, thanks, Mom.
My mom said we could steal her Jeep.
Oh, I'm riding with Sammy now. Yeah, because of what happened yesterday.
Are you okay?
I'm okay. I'm fine.
Are you sure you're okay?
You sound a little shaken.
Yeah. I mean, it was just a minor accident. Only our off the Jeep.
Only a headlight.
Yeah. And like, it's a bumper.
My parents try to tell me how to be a pilot whenever there's an accident. Like, you know, planes are like 100 times worse when they crashes.
So,
And they're trying to tell me like, but they're trying to be like, they support engineering, but my mom and dad are like small that. I was like, okay, I'm not going to start talking about the statistics from car crashes to plane crashes because everyone knows that planes are safer than any other form of transportation. I was like, however,
I really.
you guys say that instead of me being a pilot, just pick a job that flies a lot.
As soon as you really have to
Okay.
like think about it and like think about
Oh
it.
yeah, that's
More dangerous to be the pilot flying the plane than the passenger on the plane.
So
I'm the pilot, I have control.
true.
Okay.
And
they're
if you
just
know
like-
what you're doing.
And I just can't think of how the shapes would
Like,
work.
what if you're the flight
And
attendant?
rectangles.
Like,
No shit.
you can't do anything.
Any
except,
shape.
here, we'll have to crush you.
But yeah, I got
here.
21 and 25.
Life doesn't matter. Here's 2 bags
I
of
got
peanuts.
those made sense.
And
And then-
4.3?
Yeah.
I don't
Just like the
think they
planes
even
falling
do
out of
that
the sky,
in
you're
high
just
school,
doing
do
the
they?
concepts.
They
Because
don't.
you have to do reactions to peanuts.
Okay, well,
So
my
I
trip
know
to
I'm
Iowa,
doing
they
the right
handed
thing,
out
but
cheesy
then the
pretzels.
rest of it.
Really?
Here's some cheesy pretzels.
I don't
They
know.
skipped me
4.3 seemed
on the
to be-
on the way there because she ran out right after she gave the woman beside me hers. And when she came back, she
And
went
then
to
25 and 27. I don't
See,
know
on the
those
plane
graphs,
I
it's
took
like
to
nothing.
California, they didn't
25
give
is a
us anything
semicircle.
except for drinks.
So I did.
So everyone like snuck their own
Also,
food
you
onto
can
the
do,
plane.
like,
What?
just-
Which
you just
apparently
type it
you're
on the
allowed to
person,
do,
so
which I didn't know because I almost threw away my sandwich from the airport.
I know I'm not supposed to do
Yeah.
that,
But
Well,
then
you're
it's
supposed
like,
to do it for a
you
couple
can
of
buy
them,
food
right?
and take it on. You just can't
But
bring it
then-
through security.
yeah.
Because then security will.
29 lost me.
Excuse me, what is this?
We had Equifax and GFX.
Man, they didn't give you anything. Isn't that like a 4-hour flight?
Definite interval.
Yeah, so you just gotta
Five
count the
hours.
intervals.
And they gave you what airline were you on?
Like if one, so that first one went -2 to 6.
Yeah.
And then the other one goes -2 to 3. So you got to take out
I mean,
Delta.
the flight
-2 to
attendants
3
were
to
cool,
get 3 to
but
6.
Yeah.
they were funny too.
So it goes
But
Why
I
does
guess
it
it
I
was
feel
like
bad for
half the
flights.
ride.
-2 to 6.
How can you sleep on a plane? It's
And then you got -2 to 3. And this
Because
is
I
the
was
only one
tired,
you
because
want,
I had
so
to
you
get
just
up
keep
at
going
like
out.
6 something in the
That's a
morning
lot
to
easier
get
than
at the
that.
airport at like 6:50.
I would die of sleep deprivation if I had
Okay.
to fly to like Japan.
See, I'm telling you, I just can't think.
A 13-hour flight.
Yeah.
Can't sleep from excitement.
What, you're kind of the pilot?
It's good.
Kinda can't sleep. Are you gonna start with like the smaller airplanes first to get the hang of it? No, they're just gonna put you on a commercial airline. If you like to
You've never flown a plane before. No pressure. Here you go. I was actually looking into there's like a National Guard camp where they teach kids to fly.
But you don't have to join the National Guard.
Sorry.
Yeah, I was looking into that, but my
Is it-
mom's like,
They're airplanes?
but my parents are completely against me going into like the Air Force and
But you
National
wouldn't
Guard
have to join.
because they're in their words. And then my dad was, he came to a level that I can.
So Josh, what are your plans for Saturday? Are you driving or riding or
And he said even if you're in a plane, they still make you do the whole crawling under barbed wire thing.
Yeah, I'm gonna.
Just in case.
I was like, whatever. I just want to fly a plane. I want to fly the fast
Maybe I
one,
should
so I can go faster than the speed of sound.
I'm gonna fly the jets.
And he's like, you realize you don't just fly when you feel like it, and you don't just fly for fun. You fly to kill people. I was like, as long as I'm alive. I'm kidding.
Jeez.
That would be ironic after Rizzo and Jason making all those jokes that I'd be a fighter pilot if I actually came.
Fundamental hero calculus
What?
is like one of our next chapters.
Let's see what's later on in this book. Double integrals? There's double ones?
I never wrote down the notes from yesterday.
Me neither.
Oh, boy.
So we do double integrals. Lagrange
Wait, so
multipliers.
quickly explain.
Wait, this is stuff. It's hard.
Is it? Harder than sums?
Okay, this is what we did yesterday. We worked with a sine graph. And basically, we used the midpoint formula so that we would all of that, and we saw that you should get 0. Because when you have this positive area and you add a negative area, it's going to equal 0. And then we was talking about how that's also called the net area.
Yeah, so do I need to be here?
Do what the other interactions are.
Look at the cosine graph because that was the derivative. This would be the actual graph, and it still has the same thing where it's negative, and also has 0.
Yeah.
And we just went over some homework problems, like
I think I'm getting this.
this one here. It was supposed to be left and right, but we wanted to do the trapezoid one. And we literally just took the equations for everything.
Yeah.
And then you made my funny right there.
Oh yeah. You sent that in the group chat. And it's just like
It still hurts.
oh no, it's the little what does that mean?
So, we started the integrals, and basically the same thing we were talking about with that part and that interval. The interval is A, B, you just put A, B there. So, if you take this equation, it'd be just, it's just a,
It's the dx.
that's just the delta x. It's basically what we did over here.
Oh. Except you instead of
Yeah.
the delta.
Instead of having there,
Yeah.
instead of having that, you would
Morning, everyone. Let's get started, I guess.
just
So first, let's kind of summarize what we covered yesterday and finish up on that section 1.3. Examples, questions you might have on what we learned yesterday was we had a definition of a definite interval. So um, had this symbol for definite interval. And again, you read that symbol as definite interval from A to B. So you're on an interval from A to B. The left-hand endpoint of the interval as the subscript, and the right-hand endpoint of the interval as the superscript. This was the symbol called definite interval, and it is a value which is defined by how was it defined? Okay, so this is defined by what's this called?
The limit.
Defined by Riemann sum. What does the limit do to my Riemann sum? It's the number of rectangles go to Riemann sum with infinite rectangles of infinitesimal. So, by there,
Infinitesimal? Infinitesimal.
this value is the sine area between f of x and x axis.
Can you move the camera to the right a little, please? Thank you.
So we define this thing called a definite interval, which is an elongated S with a subscript and a superscript. We defined it as a Riemann sum, so there's your Riemann sum, but we also included a limit n goes to infinity, which forces the Riemann sum to fit underneath the curve to give the exact area, exact sine area. So this value is the, I guess I'll add right here, the exact sine area between f of x and the x axis. Note, if f of x is polynomial, we'll less than or equal to 3, then we can evaluate value exactly by using special sum rules. Otherwise, we must approximate using it's so low here I can't write. Using one of the special sums called like right sum, left sum, midpoint sum. So this thing called depth interval has a definition, and it gives us a number, a value. Now, we only have the knowledge at this point in time to get an exact answer when we're dealing with a polynomial that's degree 3 or smaller. Because we have some special formulas. This idea of special here, what I meant by this, just a reminder, this I'm talking about summation of 1, summation of k, summation of k squared, and summation of k cubed. So with this knowledge here, we can handle up to a degree 3 polynomial. Anything else, if it's a higher degree, or if it's not polynomial, if it's exponential, if it's trigonometric, if it's anything other than this, then we have to only approximate for now. Okay, that's kind of a review of what we've covered so far, with a little bit extra emphasis on some of the points there. There's still a couple of theorems in this section that we need to discuss that are pretty obvious, but we need to discuss them in a couple minutes. Then we'll do some examples, see what kind of homework questions. Hold on a minute. Let's put it back on this board because they may still need the copy. In case they didn't get finished copy. Leave it here on this board for a minute. I'm just kind of filling time where everyone has a chance to finish copying that notes here. All right, so we any questions on this? This is just, again, kind of a review summary, give you kind of a big picture plan of what we're covering and what we're going to be doing. Yeah, we did one yesterday. We did the sine of x.
Oh, yeah.
Yeah, we did 2 to the x or something yesterday. That was 1 minus 2 to the x. Yeah. That's exponential. So yeah, we've done exponential, we've done trigonometric, and both of those we did by approximation. Yesterday we did the quadratic that we had done by approximation initially, and then we did it exact yesterday. So I'm saying that going forward, until we have more knowledge, we can do an exact value only if it's a degree 3 polynomial or less. Everything else we're going to have to approximate. Okay, so let's look at these theorems, other theorems in the book that ought to make good sense, I think. So page 3, so I haven't write all of this down. Page 344, I'm looking at a theorem. Hopefully this makes sense. We've already talked about it. They're just stating it in the theorem for you. So the definite intervals measure sine derivative. You just kind of wrote that down here, but here's a theorem that states it for you. Definite intervals count areas above the x-axis positively and areas below the x-axis negatively. Algebraically, this means that if f of x is greater than or equal to 0 on the interval a to b, then the definite interval from a to b of f of x dx is greater than or equal to 0. So the value you to calculate for that interval would be positive or equal to 0. And vice versa, if the function is always below the axis, so if f of x is less than or equal to 0, on the interval c to d, then the definite interval from c to d of f of x dx will be less than or equal to 0 as well. So does that seem obvious to everyone? Questions on that? Mm-hmm. That's just more, to me, that's more of an observational theorem than a application theorem. The next theorem on the top of the page is an important one for solving problems. Also more of an application theorem rather than observational. And it's oddly obvious, though. So can you explain the first one for me? It said the first theorem, part of the theorem says, definite interval from a to b of the sum of two functions, f of x plus g of x dx is equal to definite interval a to b of f of x dx plus definite interval a to b of g of x. So let's hear what your thoughts are on that theorem. What does it say to us, and how could it be true? How could you explain it without doing a formal proof? What could you explain about it that makes it true? Yes, it is breaking up a sum of two functions into a sum of two different definite intervals, and as Justin said, we already learned a theorem that says when you have two different functions inside of a summation, you can split up that summation into two different summations. Well, since the definite interval is defined as a summation, then it makes sense that I can apply that same thinking and split it up. And that's how the proof would go. Literally, you would just use the definition to write this as a sum, and then use the rules about sums to split that up into two separate sums, and then use the definition to go back to decimal. Y'all visualize that?
Yeah.
Take this to a definition, which would have a summation of f plus g, and then the rule of summation says I can split that into two different sums, and now I can use the definition there to go back to it. So it's really like a two-step proof. It's very, you don't see this. Oh, look, I'm sorry, Reza has a question. Yes, Reza.
Can I ask what dx means? Is dx another function, or does it mean something else?
No, that's a good question. Dx is not a function. Good question. Dx in this realm here is part and parcel tied with. Is part and parcel tied with the symbol, the elongated S symbol in this dx. So, good question. This symbol and that symbol, with whatever goes there, they go together to indicate the idea of this, what we call an interval. In the same way that d by dx of some function goes together with talking about a derivative. This derivative, remember, was something about the limit. We didn't use this notation exactly, but this is effectively the idea that delta x goes to 0 of the change in y over change in x.
Mm-hmm.
Remember that?
So is it a derivative thing?
That was the derivative thing, and when you did that, you ended up with something called dy over dx. So this dx thing that you see here and here, that's a differential. We call it a differential. It comes from the concept of shrinking delta x to infinitesimally small. So delta x is just some fixed width And when we shrink that width to effectively 0, we call it a differential of dx. And that's what's happening here. This dx effectively comes from that delta x right there. But like in the symbol dy by dx, you don't separate those out. Those go.
Okay. Angels are getting your way.
Angels, yeah, I hear angels calling me home. So again, the dx symbol here is not a separate function. It's not a divisor. It's not a multiplier. It's just a part of a notation to indicate to a derivative. And the same thing here, this dx notation here is part of this interval notation that says find interval, find this value that's called the interval. Because I don't know if that fully answers the question, but
It's just an integral piece, like something that you write for it.
yes,
Okay.
it's just part of the notation for an interval. That is correct. Good question. It is not another function. It's not a multiplier. It's just part of the notation for interval. Everyone else got that? Good question. Hadn't really delved into that, but that is a good question. Okay. So the dx is just part and parcel to the interval symbol. We just always have it, and it disappears when you get the answer. When we get a numeric answer at the end, you don't have a dx. Okay. So we talked about this rule, which was obvious. It can be explained by the summation rules that we've seen before. The other one there is similar. If you have a constant multiplier, did they use k or did they use this one? Yeah, k. K times f of x dx. This can be analyzed when you're trying to find the value by simply taking that constant out in front of the definite interval and multiplying after calculating the definite interval, multiply by that constant after the fact. So you can multiply the function by the constant and then do the definite interval, or you can take the constant out, do the definite interval, and then multiply it later. And that ought to be obvious as well by the same thinking. This is defined, this definite interval is defined as a summation, and we had a property already that we discussed for summations that you can pull a constant multiple, you can factor that constant multiple out of the summations and multiply after that. So that explains those two terms. They're pretty obvious. They are useful in terms of when we try to evaluate definite intervals. I don't think they're that hard to understand or to use. Right? We'll do an example here in a minute, I guess, if you want. And then the next page has a theorem with some more important properties of definite intervals. First one says the definite interval from a to a of f of x dx equals 0. How do we explain that one? I mean, if you think graphically, you got some function here, and if you're going to start at, let's say, a right there, and you're going to end at a, well then, if that's as far as I'm going to go, what's the area? I'm not going all across. Well, what's delta x? If my interval is from a to a, then what's delta x? A minus a over n, which is 0 over n, which is 0. So if I multiply delta x at 0 times whatever my height of my function is, I get 0. So I think that's fairly easy to understand, obvious. One that's a little less obvious, but is still important to us, is the integral from b to a of f of x dx is equal to the negative of the integral from a to b of f of x. How can we explain that one? Right. Once again, let's talk graphically for a minute. So if I do looking at, for example, this without the minus sign, the integral from a to b of fx dx, then on the right-hand side of this equation, just this part right here, delta x equals, because this is indicating the starting point of my interval and the ending point of my interval, is b minus a over n, which is some number. Okay, well now let's go over here to this one. Now we're starting at b and ending at a. So this means on this one, delta x equals a minus b over n. So
negative makes the a positive.
exactly. So if I were to multiply, for example, either side by negative, it doesn't matter. But if I multiply this side by a negative sign, so I multiply by a negative there and negative there, then don't I get this? So this is a minus b over n. So hopefully that helps explain it. Another way to say it is, when you go left to right, your delta x is, when you go left to right this way, or this way, delta x is greater than 0. But if you're going the other direction, that's
Joe, we're having some serious transmission issues, and Dale looks like a big square.
I'm kind of a
Blurry.
big square. I mean,
A blurry
I'm a
square.
math geek and I'll own it, you know. I look like a square. How about a circle?
Not anymore, actually.
Well,
It kind of glitches.
yeah, it's getting really bad when you move, so
Just stay
Almost.
I mean, it's pretty bad. It's the worst I've seen it.
Do we need to reboot?
We need to reboot.
I think
We might need to
yes.
reboot. What's going on over all this booting up
That
over
was
here?
just a PC boot.
Well,
Y'all.
while we're rebooting, I'm just going to be saying, let me I think we're almost done, but go ahead, reboot.
Okay.
I'll try a problem. We're going to try a problem. Let me pick a problem before
Pick
she
a problem
reboots.
and
And then we'll reboot. So start working on a problem for a moment. See if you can do number, whatever. We haven't done a whole lot. How about number 41? Try 41 for a few minutes. We'll come back to it while she's rebooting.
Wow, this is a lot. Oh gosh.
Look,
Oh,
it's
wait.
us.
Who's that?
It's us.
I don't know who those people are.
I don't know.
You know what I'm feeling right now? I'm feeling Chick-fil-A right now.
But we don't have time today to go to
Well, if we finish the lab exam.
Wasn't that part of your homework?
What was homework? Okay, so it starts at the bottom thingy, right?
Of course, it'd be nice.
Right? It starts at the bottom thingy
What do you mean?
with S. The lower thingy is.
Same.
Yeah, that's where it
That's
starts.
the
It goes from
A.
A to B.
Okay. Or on the front of this.
Okay, so A. Find A
Alright, I'm trying. Hey Brittany, look what I'm doing right now.
You're not doing it. Or you? I thought we can't.
Careful, careful. You know what it is, right?
What the interval is.
You know what it is, right? Look at it carefully.
I can't even see.
It's just like the one he did.
There's a reason why.
Nice. Of
He
course.
did one just like
The only
this.
difference is.
Y'all, guess what? It's one of those sum thingies.
Yeah.
Thanks, Rachel.
Where it's like f of a plus k delta x times delta x.
I don't believe in that.
Okay, so,
Yeah.
41.
so we have to use our sum for the.
That's what it says.
40.
Could you use our sum?
We're doing 41.
Yeah, 41. Why do they want me to
Well,
use the
eventually
rats?
you're not gonna use any sums, you're gonna use integral formulas.
Holy cow, really?
That's not real nice. This is the last unit.
Well, there will be some definite integrals.
I don't believe in definite integrals.
You learn that? Isn't that where n goes to infinity?
That's what he was talking about.
The limit?
No, you're talking about, it's the ones where we were doing the rules, where it's like limit rules and derivative rules and sum rules, but not.
Yeah, so you're doing this in 3 parts, like you're doing the right sum, and then you're doing the approximations, and then you're doing the limit.
Can I not
Break
evaluate
this
this
up.
exactly?
How do we do section?
I'm serious.
Do you not want me to
You
evaluate this
do
exactly?
the sum of f of a plus k delta x times delta x.
Yeah,
It's gonna be
that's just
miserable
using the right
first
sum
3
formula,
years
right?
on state.
I'm not gonna make it too honestly.
Become an artist.
That
Halfway
a
through
plus
the semester,
k
you're
delta
supposed to go
x
business
represents
major.
your x of
I
k star.
am business.
Something easy.
So then,
So, what's the star again?
The star means you choose
I'm not
anything
smart enough for this.
within the k interval.
What does it mean?
Can you
find
hear
it
us?
without?
I don't know.
I'm so.
Somebody find a question.
that means you find it with ends. You find the sum with ends.
Okay, and we would have like, this is f of technically x, so put it.
So where the x is,
Definition.
For x.
you put,
Yes.
Nice.
and you always do it like that?
You know what?
So you'd have like the parentheses of 5 minus, and then you'd have x, which is 2 plus 3k over n,
Okay.
times 3 over n, because that's your delta x.
Wait, so is there, it's 5 minus
And that's it.
2 plus k.
3k over n. And then times your delta x, which is 3 over n.
Is that it? That's
Well,
all?
then
Or
you
do we
actually have to do
Okay, we're in. Thank you much. Appreciate it.
this stuff and get it down to all ends.
Amanda, is that better?
Yeah,
Yes.
it is.
That's great.
You better over there now?
Yes.
Yeah, I can dig
Okay,
it.
good. So what I was trying to say here is, on this theorem was, again, the direction of travel, if you will, affects delta x. And so if we're going in the standard left to right order, so from A to B, then you're going to get a positive delta x. And but if you go in the reverse order from quote big number to small number, so from right to left, then you're going to get a negative delta x. And that's why this sign here appears in that theorem. Any questions on that? That's something we can use, we'll leverage as we're evaluating. You can actually change the sign of your answer by going the opposite direction. So again, whatever the area is under this curve from A to B, if I go from B to A, it's the opposite value of it. Now the last theorem that we need to cover, and then we'll go over that problem I asked y'all to start working on, is another nice one that allows us to split up an interval in the interval. So the depth interval from A to B can be calculated as the depth interval A to C plus the depth interval from C to B for any C. And the obvious is if you have a function like this, and there's A, there's B, you know, if I pick a C here, then it seems obvious that if I do the area from A to C,
Yeah.
I add that to the area from C to B,
You're
and
right.
that's the same as the total area from A to B.
Also, why is C in
But the
between?
theorem says any C.
It's like the most inconvenient thing.
That means C does not have to be between A and B.
Oh.
How does that work? So if I have this same type of function. And this time, though, for argument's sake, I'm going to say here's A, and I'm going to stop my B right there. So there's B. So the area I'm concerned about, like over here, the area I was concerned about was from A to B. That's the left side of the equation. So the area I'm focused on is that. But how can it be that I can use and go all the way out here to C? How can I go all the way to C and get the same area by going from A to C and then from C to B?
I mean, it still makes sense.
So you're subtracting it.
Because if you go from A to C,
It'll be
Yeah.
positive.
you're getting some, on this picture, positive area. But if you go from C to B on this picture, then that's actually going to be a negative area because you're going backwards. So you take the big area minus the small area back to where you wanted in the first place. Are we following that? And that would be true for, again, for any C, whether the C is inside the interval, which is very obvious, but even if the C is on the right side or left side, it doesn't matter. It still will hold true because of, again, thinking about this and that go together. Okay, those are the last theorems. There's a theorem on page 347. I don't think you don't need to know that because we can handle all of that based on what we've already said. So I'm not even going to worry about theorem 4.13. So we're done with all the new theorems, new material. Now all we have to do is practice a bunch. So I asked you to try 41 before we had technical difficulties. So I don't know how far you got on that, but let's see. How did you do?
Well, I mean,
So what was the interval given that you're supposed to evaluate?
For 41.
Okay. And how are we supposed to evaluate?
Because the general and not song simplify it. So it's 10 to 100 and 1,000. This is not like technical standard practice. Going to be not technical.
Part of 100.
Yeah, or
R of 1,000. And effectively, R of infinity. It's not really a good notation, but then it n goes to infinity. R notation. This is just a formula that's going to calculate whatever I want. It's going to calculate an approximation in part B, a better approximation in part C, and the exact answer in part D. Okay. Just for curiosity's sake, I want to know what the picture looks like. Just this, I roll that way. So what does that picture look like?
Is it going to be diagonal?
That's right. It starts at 5, has a slope of -1. Probably a 5 there. And we want to go from 2 to 5. So we're focused on from here to 5. Well, I think I can get that area without doing anything.
Wow. Let's do it.
I can get this exact answer with not a whole lot of difficulty, I believe. Let's predict, and then we'll do it the calculus way. Let's see if we can get the exact area. How would I get that exact area without using any calculus whatsoever?
You can use trigonometry.
Right. I could predict I wanted part D
Boys, Tom talking about it.
area is equal to 1/2 of the base times the height, which is 1/2 of that base looks like a 3 to me. Now I just got to figure out the height. How do I figure out the height?
Pythagorean theorem.
I plug in 2 into this function.
Well, not that too. No, this one.
5 minus 2, which is a 3 again happens to be. So that's 1/2 of 9, I guess. So 9/2. I think the answer is 9/2 when we're said and done. Okay. Now let's do it. What was directed is in calculus, just so we can practice that a little bit. So we need to find R, a right sum of n rectangles to represent that. Right sum of n rectangles. Must have a sum. But n is undefined, it's just a variable n, so I don't put, if it was right sum of 100, I'd put 100 on top of it, but it's n. How do I do a right sum?
What was it? F of x of k times dx.
F of x of k times delta x.
Balling just from memory in this piece. Daggone.
So it's
Everybody understands why it's x of k here. Not x of k minus 1 or whatever. It's x of k, which is always the right end of things. Good. So now, that's a good first step. Now what? Yeah, we need to convert, in order to get a formula in terms of only n, you have to convert this so that the x of k is calculated based on k. That's just a plus k times delta x times delta x. Both those are different ways of saying right sum. And you need to understand both of them. Recognize. Now we just got to fill in the pieces. So what do we have over here? We have a is 2, and a b is we have that means a equals 2. It means delta x is 5 minus 2 over n, which is 3 over n. So this becomes f of 2 plus k times 3 over n times 3 over n. Okay, so all I did was replace the symbols a, k, and delta x by what we've got over here, and k is just the variable of the summation. So, what does it mean to do f of 2 plus k times 3 over n? Yeah, we use the function, so that's just 5 minus the x value. The x value is 2 plus k times 3 over n. And then that has to get multiplied by 3 over n. At this stage, we have a summation that is a function of k that has some n's in it. So we could now and need to use the special summation formula that we talked about earlier by doing some rearranging. We can use some special summation formulas to calculate a formula only in n. So let's distribute and get things kind of cleaned up inside here. let's see, I got a 5 minus a 2, which is a 3. And then that's going to be multiplied by 3 over n. So apparently I have a 9 over n sitting there. And then minus, I have a k times 9 over n. So 9 over n, actually 9 over n squared this time, times k. Or just distributed, combined like terms type of thing. Now I can use some properties of summations. Properties of summations allow me to split this up into separate sums. So I can have summation k equals 1 to n of 9 over n, and then minus the summation k equals 1 to n of 9 over n squared times k. I could have done it at first, but I'm going to do it at the end. It doesn't matter. The question up here, David's heard this, just asks, could I have just factored out this 3 over n at the beginning? And the answer is yes, I could have. This time, for whatever reason, I chose to distribute it in, and now I'm going to do the factoring after. So on each of these, I'm going to factor. So this is going to be 9 over n is constant relative to k, so this is 9 over n times the summation k equals 1 to n of 1. Then 9 over n squared is constant relative to k, so this is summation k equals 1 to n of k. So yeah, there's different ways of getting there. It's not just one kind of factor. Yeah, and when you split it with the yeah, because it would have been out here, so I had to put it on both. Okay, so this becomes 9 over n times n. And this is 9 over n squared times n plus 1 over 2. At this point, I would just clean it up a little bit more, and I'm done. This is the major part of the work of any of these problems, is getting it down to here. Let's see, so if I was going to simplify it, I'd want it as a one fraction. That would make it easier for me, I think. So common denominator looks like a 2n squared. So it looks like I need to multiply this one by 2n. So that's 18n squared minus, what is that? 9 times n squared plus n over 2n squared. And finally, combine like terms, 18 minus 9 is 9n squared minus 9n over 2n squared. So that little number down there at the end, that little nice little final answer, will give me the definite interval approximated at any degree of accuracy in one, or even exact if I let n go to infinity. So we've converted from a function of x to a function of n. So this is a function of n that represents the area under the function of x. Mm-hmm. Okay. So I can now, that's part A. That was part A. So now it's easy to do part B and C. Just plug in whatever you need. R100 is whatever that is at 100. Blah, blah, blah. I'm not looking. 90,000 minus 900 is 89,100 divided by 20,000 is 4.5 is our target. That'd be close to 4.5.
You want decimals or some kind of fraction thing?
Or yeah, decimals fine. What do you have?
I got 4.455.
We'll round to 4.46. Okay, good. Let's see, that's pretty close to 4.5, which was the exact answer over there. Let's see how much for. Well, we might need 3 more decimals. Let's get a couple more decimals. 4.55. Well, give me 4 decimals.
No, I only got 3.
Only got 3. Okay, we'll stop there. So, what is it at 1,000 now? Do the same computation. Put in 1,000. Hopefully that's pretty close, but that's not exact.
I'm so close. What?
4.4955. That's real close. That's real close now at 1,000 rectangles. So our rectangles have fitted in better when we got 1,000 of them. Before I do the final problem, let me just stop and analyze. Let's take a look over here. Let's go back. We've got a 4.455. I got a 4.955, which is even closer. Let's go back to the picture on that. Tell me why. This is a serious question. Why will any number of n you plug in over there is always going to be a little bit low. It's always going to be smaller than this number here. Why is that true on this problem? Not every problem in the world, but on this problem in particular, the way we set it up, there's something about it that no matter what n you plug in, you're going to be a little bit below that number every time. Why? It's a right sum, and how does that affect a right sum? How affect this? Yes. It's a right sum, and when you make your subdivision, you're picking the right edge, and that rectangle is always going to be below that. What about the function tells me it's always the right sum is always going to be below? What can you say from precalculus about this function that tells me the right end is always going to be below?
It's
Called a decreasing function.
E to B.
Decreasing the right end is always low. But the left end on a decreasing will always be high. Reverse it to increasing, you reverse the left and right poles. You clear on that?
So with the left,
Yes, if we've done the left sum, all the answers would have been, because this is a straight line, so they're going to be symmetric, I would have been the same amount high on the left sum as I was the right sum.
I'm more of a midpoint man myself.
Anyways, that's something to think about, because 2 of the things we covered were lower sums and upper sums. We haven't done a whole lot with that, but if I ask you for a lower sum on that picture, you've got to do a right end.
Oh,
If I ask you for upper sum on that picture, you've got to do a left end. Are we clear? You got to be able to do lower sum and upper sum, and that's not telling you which type to do. You got to think about the shape of the graph. Are we clear on this? Okay, let's do the final one. The final one is R. Limit n goes to infinity. R of n. Limit n goes to infinity of this function 9n squared minus 9n over 2n squared.
What a catch. 6 feet of jeans.
What do we do with this? Now, if you try to plug in infinity, you're going to get infinity over infinity, so it's going to be, I can apply L'Hopital. We've done this at least once.
The hospital.
And so that gives me limit n goes to infinity of 18n minus 9 over 4 n. That's still determinant, so I can do L'Hopital again.
The hospital.
It gives me 18 over 4. Since that has nothing to do with n, then the answer is just 18 over 4.
Just
Which
4.5.
reduces to
4.5. Woohoo! Or 4.5.
And you need to be able to handle all of that. Problem. Again, this was a polynomial of degree less than 3 or less. It was a degree 1 polynomial, so I can apply my special summation rules to get that exact answer. If it had not been polynomial, if it had been sine of x, which we did the other day, if it had been exponential, which we did yesterday, you would have to only approximate. You couldn't do it with these special. I would not be able to do this rule here and that rule there, unless it's polynomial.
Got him.
Okay. Other problems that we should attempt real quick, so you can have some time to practice at home. Let's look at exercise.
Really?
Wait a second, what's dinner gonna be? Guess Wendy's alone.
How about
Sitting basically.
Turns out it's really simple and I just can't think of how o'clock at night.
What are we doing for lunch?
What do you? I think it's been mine today.
all right, first number 32, exercise 32.
That's not an odd number.
Oh, you're right. Oddly, you're right. Oh. But even though you're right, you can still do it.
Man, that was a 2-in-1.
That was, I'm on a roll. Don't get me started. I'll be here all week though. Don't worry. Okay, what did we say? 32. So we're given on this problem. We're gonna look at the givens. Make sure we're using them. Given that the depth interval from -2 to 3 of f of x dx is equal to, giving me the answer is 4. And then they're giving me that the integral from -2 to 6 of f of x dx is equal to 9. And then they also give me some other information, a bunch of it. -2 to 3 of g of x dx equals 2. And then integral 3 to 6 of g of x dx equals 2. No, it's 3. I did everything right now?
Sure.
I don't have my givens correct. I can't get my find. Okay. We're supposed to find the definite interval from 3 to 6 of 2 times f of x minus g of x.
So it means we're looking for the limit.
So, in order to do a problem like this, the whole point of this problem is to practice some of those theorems that we just went over a few minutes ago. Instead of having to get into the nitty-gritty of calculating a number like we did a moment ago, you're given the numbers, you just have to fit it together using the theorems we just went over. To do that, I would suggest using the theorems to split this up into pieces that fit with the givens. So this can be rewritten as 2 times the interval from 3 to 6 of f of x dx minus the interval from 3 to 6 of g of x. All I did there was the sum rule and the constant multiple rule. So this was the sum and multiple. That theorem that had those two in it, I just applied both of them, split up this into 2 pieces, and then pull out that constant multiple. Now I've got it down to what I would call an atomic level of depth interval, and I can try to match it up to what's given.
A what level? Atomic. Wow.
Unfortunately, the interval from 3 to 6 of g of x dx is given right there.
That's
So
3.
that's 3. So this right there can substitute for here. Okay, so I don't have to worry about that one right now. That's a 3. But what about this?
What about that?
Yes. I can rewrite this as
Oh my gosh.
Integral 3 to -2 f of x dx plus the integral from -2 to 6 f of x dx. So the last theorem, I'll call it the split theorem,
That's a good name.
allows me to split a definite integral at any c value. So I have 3 to 6 on f of x. I chose, for some reason, to split it at -2. So notice the split rule says if you have an A and B here, then your first A here and your last B there have to be the same as these. And this number has to be some number C, any number you want to pick. I picked number -2. So y'all with me? This has to go 3 and end at 6 because that's where you started. And I split it at -2. Why did I pick -2 as my split?
So the right one can match with not.
Now let's see if we can match it up. I got -2 to 6. That one's, so this one is right here. But this one is related to that.
It's close.
Okay, so this is a 9. I can put a 9 in there and -3.
Oh crap, y'all.
This one, in order to use that, I need to rewrite it. So this is the negative of integral from -2 to 3 of f of x dx. So if I switch this order of the limits on my integration to the opposite, I have to have a minus sign. That's what one of the theorems said. So I don't know what they call it. Let's just call it opposite order.
Aww.
And now this is one of the numbers given in the givens. So this is that, except for minus signs. And so now we have 2 times the minus of 4 plus 9 minus 3. That's easy.
It's -13.
No.
What?
No.
What?
Because that's 5. What's 7?
I think so.
Wait.
Parentheses
yes.
first. I wonder how this math
You know what?
contest is gonna go.
Pretty poorly.
It's -13.
Got him.
Let's look at what other questions. I think you should try another one that's finding the exact value or maybe approximating and the exact value. I think you need to practice one where you get the exact value by doing the limit and everything. So let's like practice on, how about number 50? So take a few minutes now and seriously put some time and thought into doing number 50 and getting an exact answer.
That's not either.
And I'll give you a couple of minutes, and I'm going to start writing as well, but try to not just copy. Try to do it yourself and then check your answer when you're done.
Yeah, let's try doing that ourselves.
Right. Use property.
Okay, y'all, let's get this. Are they cooking back there?
Yes.
They're making jambalaya. Stir up the jambalaya.
Oh, cooking is it's like cooking.
Oh yeah. So,
Oh, well, nice to use that.
yeah. What is happening over there? I don't think this is right, but I'll stick with it. What's he doing? I did not kill that
I
approach.
did this.
Yeah, same.
Did you get this?
I got 38. Let's see what we got here.
I could have done something like that.
Oh yeah, that'd be
This is
27.
27
Yeah,
because you
yeah.
cube it.
So 27 minus 1 would be
26,
6.
which is just that.
Let me fix that. Hey, I got 0. No,
I hope it's right.
I think it's right. Unless the book's deceiving us. Okay. When did you watch Ratatouille?
When?
It was a long time ago, right? Was it good?
I loved it. You should too.
I really should watch Ratatouille. I'm missing out. Have you seen Wall-E? It's a really nice one.
You already finished, Rachel?
Yeah.
You did all of this?
I did a different approach. I used the theorems on page 347, which is what they said to do.
The directions for that, you're right. I didn't intend for you to do it that way, though. But that's fine.
I'm sorry.
But that's fine. Make sure you know how to do it this way, though, too.
Okay, I'll write that down as well.
That would be a lot easier.
Terrence.
And I grant you, those theorems give you a quick shortcut because you need to prove those theorems are true. We didn't prove those theorems are true. We didn't even discuss them, so using it is a little bit cheating. You can prove them easy enough. You can prove them easy enough.
I'm sorry.
What did we do?
Should be right there what the man says. Wait, so do you not want me to use those theorems on the test, Mr. Gaddis?
Well, you can use them on the test, but you have to prove them, turn in your proofs.
Do you want me to turn in my proofs like with my test? Or are you saying it's a supplementary thing?
I mean, if you're gonna use them, you gotta prove them.
Wait, so what's the answer?
What's the answer?
You got it.
I don't get it.
Proving on this is just a matter of doing this algebra on a generic function. That's not that hard. It's just doing the algebra.
Oh,
Write these proofs, kids. Well, half depends on it.
Yeah. Well, I didn't do it, right? That's how I thought.
Yeah, it's like, hang on a second.
At least I couldn't go past that. But sometimes I didn't realize that. I didn't go out. I was gonna go, this isn't right. This is actually a good spot. It's not how it's fun. What did I do wrong? I did something wrong.
Is he underwater? Let's get. Go on. Got 5 minutes left. Got 5 minutes before the reckoning.
We're out of time?
Yeah, we just have to flash from the system.
Okay. I guess we're out of time. So we'll pick up on Monday, do some homework, practice on all of this. We'll pick up and see what questions you have on Monday. On the 3 sections that will be covered on the test on Tuesday.
Test on Tuesday. Prepare yourself. Guess what?
Oh, I think I did it right, but let's make sure.
I'm testing in an hour.
This,
Exams.
1 plus 1 is 2. And then you've got 2 over n times k squared that. Multiply times 2 to 4.
Fred,
And then the math is when you multiply the 4 over n.
yeah, I looked at
Another 4 over n times k.
like Grammarly papers and checked over that. We missed like 2 commas, but otherwise, my
And when I first did it,
We missed like 2 commas.
yeah, I'm pretty pleased, honestly.
I got stuck. I was like,
I don't think he would count off for those 2 commas. He's a science teacher, not an English
I
teacher.
mean, he probably won't even pay attention unless he's using that turn it in.
You know what stinks?
What?
I just found out I have to take the SAT subject test.
Why?
For MIT.
Ew.
No, why would
Which
they do
ones?
this? I have to take one math and one science. I said I don't enter the levels on math and or what type of science.
That's gross.
I haven't taken biology in a year and I don't want to do that. But at the same time, I'm really terrible in chemistry. I don't want to take that either. So I don't know if it was science. I'm not going into the science field.
Imagine Dale skateboarding.
I'm into the math field.
Imagine
I mean,
meeting Dale.
And the worst part,
Should I bring like ravioli in my pocket when I meet him?
scores are not in
beans.
the range of
Oh,
MIT
beans in my
They're the
pocket, and
one
I just
right
scoop out my
under
pocket and
it.
start eating them.
Yes.
Literally right under it.
You
If I don't
the
get it
spoon
on
in your
that,
pocket,
I'm
and
really
then offer him beans.
then at the
I'm
same
like, hey
time,
Dale, you want this?
those ranges show averages, which means someone had to have gotten something lower.
Brittany, my plan is I'm gonna have ravioli in my pocket when I meet Dale. And then when I meet him, I'm just gonna take it out and put it.
Right, that's where all that
Hey
came
Dale.
from. So now you're here.
Do it.
None of us should call
But all
him
of that is
together.
multiplied by the two.
Why?
We should just all call him Dale when we meet him.
Why?
Because
So I
it'd be
pull out the
funny.
tutor, and you don't have to worry about that.
Like that.
I know.
we would all fail the class after that.
Oh yeah, totally.
And I kind of, like I do this
If
all
we're
in
not
step.
already.
You have to-
Those that aren't already fit.
And then
What'd you
this
say?
is just a constant, so you can imagine it going up there. And so this would be 4n. Right, the sum of 4 would be 4n. It would be 4 sum of 1. And then this would be 8 over n times the sum of k, which is the n times n plus 1 all over 2. And then this one would be 4 over n squared times the sum of k squared, which is the n times n plus 1 times 2n plus 1 all over 6. And now you have these fractions to deal with. And so then, so I would go ahead and multiply all this out. So that's n times n squared plus, check that, that's 2n squared. Plus 3n plus 1. And then you multiply through the n. So now you've got, just leave it like that. And then you've got an squared plus 8n all over 2n. Plus, and then you've got to multiply through that, so you've got 2n cubed plus 3n squared plus n, right? And then times 4, so then you've got 4n cubed plus